OCR A-Level Chemistry, Paper 3 for 2017. There's no multiple choice for this one, so let's just get right on into it. So, within the permafrost in Arctic regions of the Earth, large amounts of methane are trapped within ice as methane hydrate. Methane makes up about 13.4% of this mass. Scientists are concerned that global warming will melt the permafrost, releasing large quantities of methane into the atmosphere. The HOH bond in ice is about 109, but about 105 in gaseous H2O. Explain why there's this difference. So if we're looking at 109, we're thinking that's got to be tetrahedral. So it's got to have 4 bonded regions. Whereas in 105, well, that's going to be non-linear, which is 2 bonded regions and 2 lone pairs. So how is that possible if we've got the same molecule? Well, if we take our water molecule and we pretend that it's in a solid state, what's going to happen is we're going to create hydrogen bonds. Sorry, give me a second. I'm a much faster speaker than I am a writer. We're going to create hydrogen bonds, which I'm going to do in blue, between the lone pairs and the hydrogen atoms on the water. And what's that going to do? Well, it's going to hold it in place, and it's going to act like more bonds. It's going to act like a bond on each lone pair, so there's 2 more bonds. So, whereas in gas, you've got OH, it's 2 lone pairs there, hydrogen there, and hydrogen there. But the water molecules in the gas are so spread out, so separated, that you can't have a hydrogen bond that's all the way there. That's not going to work. So we're going to say the intermolecular forces in that are negligible. They're basically 0. They're not worth our time, to consider. So what are we going to say? Well, we're going to say our hydrogen bond between the lone pair and hydrogen atoms in ice act as third and fourth, act as a third and fourth bonded region creating a tetrahedral shape. Full stop. Whereas in gaseous H2O, intermolecular forces are negligible. They really need to put more space on these. Are negligible, and so the lone pairs repel the bonding electrons. I've got to move this down. Repel the bonding electrons more to create a smaller angle. Why are scientists concerned about the release of methane into the atmosphere? Well, hopefully you know this from year 7, 8, 9 GCSE chemistry. Methane is a greenhouse gas. Nice and simple, 1 mark. Determine the formula of methane hydrate. In the formula, show the value of x to 2 decimal places. We can do that. Right, so I remember from the question earlier, methane makes up about 13.4 of the mass of methane hydrate. So we're going to do our MRN grid, and we're going to do CH4 H2O. So we're going to pretend we've got 100 grams of it. So methane makes up how much? 13.4 grams of it. So if we've got 13.4 grams in 100 grams of methane, then 100 minus 13.4 gives us 86.6 grams of water. And then MR of water is 18, MR of methane is 16. So 13.4 over 16 gives us 0.8375, and 86.6 over 18 gives us 4.81. Now we divide by the smallest number to get our ratio, so that's going to be 1, because 0.8375 divided by 0.8375 is 1, and then you do 4.81 over 0.8375, and that is 5.7. So 2 decimal places, so 5.74. So we need to write out the whole formula. So it's going to be CH4 dot to denote loose connection, 5.74 H2O. That looks suspiciously like an H, so let me just... It's a 4. There are not 3 hydrogens in water. There you go. Calculate the volume of methane in decimeters cubed. Decimeters cubed. That would be released from the melting of each 1 kilogram of methane hydrate at 101 kilopascals and 0 degrees Celsius. So we've got pressure, we've got temperature, we've got temperature, we've got volume, well, we're finding volume, and we've got a mass. So what are we going to do? We're going to do our PV equals nRT. So first of all, we've got to convert T. T should always be in Kelvin. So we've got 273 Kelvin. Is that right? Yes, it is. Awesome. So 273 times 8.314, that's your gas constant. That is in your formula booklet, times number of moles we've got to find next is equal to our pressure, which is going to be 101 times 10 to the 3, because it's got to be in pascals rather than kilopascals, multiplied by our volume, which is what we're finding. Now, just a quick thing. Volume is going to be in meters cubed. That's just how it comes out, so we've got to convert that at the end. So, let's find our number of moles. So, what is the molecular mass of this molecule here? So, we already said CH4 is, I've forgotten, 16, there you go, 16 plus 5.74 times H2O, 18, which gives us 16 plus 5.74 times 18, 119.32. So our number of moles is going to be M over MR, so it's going to be 1,000 grams over 119.32. So number of moles is equal to, let's just leave it as that, 1,000 over 119.32. So then we've got to rearrange. So V is going to be equal to 1,000 over 119.32 multiplied by 8.314 times 273 over pressure, which is 101 times 10 to the 3, and that's going to give us our volume in meters cubed. So, give me a couple of minutes just to type this into my calculator. 119.32 multiplied by 8.34 times 273 all over 101 times 10 to the 3 gives us 0.1889, etc. So just call it answer. And then we've got to do answer over 1,000 to get us our decimeters cubed. No, that's absolutely wrong. Don't listen to me. We've got to do answer times 1,000 because we're going down into decimeters cubed, so we're making it a bigger number. So our answer times 1000 gives us 188. What does it say? 3 significant figures, so 189 decimeters cubed. Suggest why some industries are interested in the presence of methane hydrate in regions of the Earth. Well, why is anyone interested in methane? It's good fuel, so all we have to put is for fuel. Nope, that is not how you spell fuel. For fuel or energy consumption. A student plans to determine the enthalpy change of reaction 3.1 shown below. This enthalpy change can be determined indirectly using Hess's law from the enthalpy changes of reaction 3.2 and 3.3. The student will determine the enthalpy change of reaction 3.2 as outlined below. Weigh a bottle containing sodium oxide and weigh a polystyrene cup. Add about 25 centimeters cubed of water to the polystyrene cup and measure its temperature. Add the sodium oxide, stir the mixture, and measure the maximum temperature reached. Weigh the empty bottle, weigh the polystyrene cup with the final solution. That gives us a bunch of data. Well, what are we going to do with this data? We're going to turn it into something useful. So the mass of our bottle plus our sodium oxide minus the mass of our empty bottle is going to give us our mass of sodium oxide, which is 1.24 grams. Mass of the empty polystyrene cup versus the mass of polystyrene cup plus our final solution, well, if you minus the top one from the bottom one, it's going to give you the mass of the solution, which is 47.33 minus 21.58 gives us 25.75. And initial temperature readings, well, it's going to give us a change in temperature readings, which is going to be 35 degrees Celsius. The density and specific heat capacity of the solution are the same as for water, so all that means is 1 gram is equal to 1 centimeters cubed, and specific heat capacity is equal to 4.18. So what we're going to do, we're going to calculate the enthalpy change of reaction 3.2 and the enthalpy change for reaction 3.1. So let's go to work. We have to do reaction 3.2 first, because I don't know if you realised, in the question it says you need to work out 3.1 with a Hess cycle. So 3.2, we're going to do it the old-fashioned way. Q is equal to mc delta theta. All that means is our change in energy is equal to our mass times our specific heat capacity times our change in temperature. So Q is equal to our mass. We're going to do our mass of our solution. We are not going to do 1.24. We are going to do our mass of our solution, because our solution is this bit here. And that's what we're measuring the enthalpy on. So 25.75. 25.75 times specific heat capacity is the same as water, 4.18, times change in temperature, 35, gives us 25.75 times 4.18 times 35, gives us, very slow typer, 75 gives us 3767.225 joules. Now, we need to convert that into kilojoules, so we're going to divide it by 1,000. Why? Well, because enthalpy is measured in kilojoules per mole. So we divide that by 1,000, we're just going to have 3.767225 over our number of moles is 1.24. That's our mass of our sodium oxide over our molecular mass of sodium oxide, which is Na2O. So sodium is 23. Times 2 plus 16 gives you 62. So then you're going to do 1.24 over 62. So then you do 3.767225 over 1.24 over 62, and that's going to give us 188.36 kilojoules per mole. Make sure you get your units in there. So that shouldn't be a plus, that should be minus 1. So what are we going to do for reaction 3.1? Well, if we go back to look at what it was, because it was a while ago that we looked at it, we have got sodium oxide plus 2 hydrogen chloride gives us 2 sodium chloride plus water. Well, hang on a second, because sodium oxide, water isn't relevant, hydrochloride, sodium chloride, and water. So if we combine these two equations somehow, we'll be able to create the equation at the top. So what are we going to do? Well, we're going to cancel out some stuff, but first we need to make them equal to each other. So what we're going to do is we're going to times reaction 3.3 by 2. What does that do? Well, it's going to put a 2 there, it's going to put a 2 there, it's going to put a 2 there, and a 2 there. So what does that do overall? Well, our 2 sodium hydroxides cancel out, and one of our waters cancel out. So that becomes, overall it becomes Na2O plus 2 HCl gives us 2 NaCl plus H2O. And that is exactly 3.1. So the reaction is combined 3.2 and 2 times 3.3. So all we have to do is add up the enthalpies for these two reactions. So remember, minus 57.6. So minus 57.6 times 2 plus minus 188.36. That should be minus, sorry. It's exothermic, it's giving off energy because it raises the temperature, so it needs a minus in front of it. I should have made that clear when I did it, I'm very sorry. Gives us our enthalpy, there it is. So, minus 57.6 times 2 plus minus 188.36 gives us minus 303.56 kilojoules per mole. And then just underline that one as well. And our sign in this one, at least, is correct. It is in the other one now, but I should have spied that sooner. I'm very sorry. The uncertainty in each temperature reading is plus or minus 0.1 degrees Celsius. The uncertainty in each mass reading is plus or minus 0.005 grams. Determine whether the mass of sodium oxide or the temperature change has the greatest percentage uncertainty. So how are we going to work out percentage uncertainty? We do uncertainty over our value times by 100. So what they'll trick you up on here is that our temperature reading and our mass reading were both about change in mass and temperature reading. So our temperature reading, our change in temperature, was, don't know where it got that from, delta theta was equal to 35, and we had to do a sum to do that. We had to do, I don't know what it was, let's just pretend it was 55.5 minus 20.5. Okay, and then the uncertainty in the mass, I'm not even going to bother trying with that one, but you get the idea. It's like this one. So what are we going to do? Well, we're going to do our uncertainty, but because we had to do two measurements to find the change in temperature, it's going to be 0.1 times 2, because you could have got it plus 1 the first time and minus 1 the second time, so the greatest variance is plus or minus 0.2. over our actual value, which was 35. Let me just check that. Gosh, it's a long question. 35, awesome. So that gives us 0.1 times 2 over 35 times 100. I didn't write that in. Times 100 gives us 0.57%. And then we're going to do our change in mass. So we're going to do the same again. 0.005, be careful with those decimal places, times by 2 over our mass reading, which was 1.24 times 100, which gives us over 1.24 times 100 gives us 0.8 rounding 1%. So which is bigger? Just write this in: temperature, mass. So mass has the greatest percentage uncertainty. Now you'd find that anyway, if you didn't do times by 2 times by 2, but you wouldn't get 2 marks, you'd get 1 because you did the maths incorrectly. So just make sure you go back and say, where is it? That's too far. Make sure you go back and say, well, I'm doing change in mass here, so I have to do the uncertainty twice. I'm doing change in reading in temperature here, so I have to do the uncertainty twice. It's all about, first of all, practice, and second of all, noticing small little details that they'll try and trip you up on. Suggest a modification to this experiment using the same apparatus, which would reduce the percentage errors in the measurement. Or if we have to use the same apparatus, how are we going to reduce the percentage error? Well, we're just going to use a larger mass of reactants. Larger mass, name your reactant, of sodium oxide. And what this will do in this is give you a larger temperature change. This will create a larger temperature change. I'm just going to put delta T for time, and this reduces percentage uncertainty. Sodium oxide can be prepared by the redox reaction of sodium nitrate and sodium metal. Nitrogen gas is also formed. What is the systematic name for sodium nitrate? Well, I've just said it. It's sodium nitrate. But before you start going, haha, easy, 1 mark in the bag for 2 words, there is a little bit extra. Nitrogen can change its oxidation state. So what you have to do is you have to go nitrogen and oxygen. Well, sodium is going to be +1, and oxygen is going to be -2, and then we've got 2 lots of them, so it's going to be -4. So sodium's +1, and nitrogen is, let me just rub that out so I can write it in clearer. If oxygen's going to give us overall -4, what do we need to make a non-charged molecule? Well, nitrogen needs to be +3. So we're going to put 3 in Roman numerals in brackets after the name. Using oxidation numbers with signs, show the element that is oxidized and the element that is reduced in this reaction. Well, it's given us all we need in the question, so all we need to do is write this out properly. So we're making, that's a poor place to put it, we're making sodium oxide, and how are we making it? Well, the question says with a reaction of sodium nitrate and sodium metal, and then nitrogen gas is also formed. Well, we've just said that nitrogen up here is going to be +3, and well, in an element it's always 0, so we know that nitrogen is reduced. So we have to put nitrogen in here. Oxidation number change from +3 to 0. Elements are always 0. And on that note, we've got sodium here, which is 0, and it's changing into +1. So +1, which is sodium. Lovely. And just a quick note. Yeah, you know it's oxidized because the number increases. You know it's reduced because the number reduces. Nice and simple. Construct the equation for this reaction. Well, hell, we've already done this. So NaNO2 plus Na gives us Na2O plus N2. So we want to use our oxidation numbers because we have sodiums even literally everywhere. One here, one here, one here. And it will get very confusing to balance the old-fashioned way very, very quickly. So what's our change for our reduction? Well, it's going to be -3. And now we do our oxidation. So for sodium, we know it went from 0 to +1. But we've also got a sodium here that was already +1. So what are we going to do? Well, we're saying that in order to go from 0 to +1, it had to +1. But also, to go from +1 to +1, it had to have an overall change of 0. So what are we going to do? Well, we're going to average it out. So what's +1 plus 0 over 2? Well, it's a half. So overall change is a half. So how do we make a half equal 3? We times it by 6. So we're going to put a 6 in front of our sodium. And then we want to balance our other stuff. Nitrogen is 2 on the product side and only 1 on the reactant side. So we need to put a 2 there. And now we can do any other trivial balancing. So sodiums, we have 2, 6 on this side and 2 on this side, but what are we going to do? We're going to put a 4 here. So now we've got 8 on this side and 8 on this side. Nitrogens, we've got 2 on this side, 2 on this side. Oxygens, we've got 4 on this side, and would you believe it, 4 on that side. So this is our answer, so just write it nice and neatly on the line. Na plus 6 Na gives us 4 Na2O plus nitrogen gas. This question is about reactions of hydrogen peroxide H2O2. Hydrogen peroxide, iodide ions, and acid react as shown below in this equation. A student carries out several experiments at the same temperature using the initial rates method to determine the rate constant K for this reaction, and the results are shown below. Determine the rate equation and calculate the rate constant including units. Well, we always know that rate is going to be equal to some constant, rate constant, times concentration of A to its order, call it M, times the concentration of B to its order, etc., etc. So, what are we going to do? We're going to use these changes in concentration to find the order of each and every reactant. So, if we go to the table, we are doubling the concentration of our iodide, and we're also doubling our rate. So what does that tell us? It tells us iodide is first order. So then we go back and we say next one that changes is hydrogen peroxide. But just look out because they've turned this back, right? So you don't want to do 3 to 2, you really want to do 1 to 3. Where are these boxes coming from, man? So we've doubled hydrogen peroxide. What change does it make from the all the way at the top, well, it times it by 2. So we've doubled the concentration of hydrogen peroxide, we get double the rate, so hydrogen peroxide is also first order. And then finally we get to do our last one, which is our H plus ions. So where do we go from here? See, this one, 3 and 4 are the closest, except for the last column. So we've doubled it here, but no change has taken place. No change has taken place. Well, in which case, it's 0th order. Changing concentration hasn't affected rate, so it has to be 0th order. And it's not going to feature in our rate equation, because in our rate equation, if, like we said earlier, rate is equal to, let's use our real examples because we're going to do it in a second, it's some constant, concentration of iodine to the power of 1, concentration of hydrogen peroxide to the power of 1, because they're both first order, times the concentration of H plus to the power of its order is just 0. Anything to the power of 0 is 1, and timesing things by 1 doesn't do anything to them. So there's no point in having it in the rate equation. So we're saying rate is equal to some constant times our concentration of iodine to the power of 1 times our concentration of hydrogen peroxide to the power of 1. Well, if you do times to the power of 1, nothing happens to it. It's just what it is. So then we're going to pick any rate at all from the question. I'm going to pick the first one. So 2.00, watch out for your units up here. So 2.00 times 10 to the minus 6 over our concentration of iodine at that point, which is 0.01, multiplied by our concentration of hydrogen peroxide at that point, which is 0.01, and that's going to give us our rate constant. So 2.00 times 10 to the minus 6, answer over 0.01 times 0.01 gives us 0.02. So K is equal to 0.02. But don't forget, question asks for units. How are we going to work out units? Well, rate is always equal to moles per decimeters cubed per second, over one concentration, which is moles per decimeters cubed, and another concentration, which is moles per decimeters cubed again. But if we have it on the top and we have it on the bottom, we can cancel it out. So we take out that moles per decimeters cubed, we take out that moles per decimeters cubed. So that leaves us with seconds to the minus 1. That leaves us with seconds to the minus 1. Pens stopped working. That leaves us with seconds to the minus 1, there it is, over moles per decimeters cubed. Well, if we have it over, then we can just move all of these to the top and put their powers to the minus 1. So seconds to the minus 1, moles to the minus 1 per decimeters cubed. Minus times minus is positive. So let me leave space to write my answer. So we've said that it's seconds per second per mole decimeters cubed. But what we want to do is put it in order, so all our negative powers are afterwards. So it's going to be decimeters cubed per mole per second, and our value, which was 0.02. Make that a little bit clearer. The rate constant K for this reaction is determined at different temperatures. Explain how the student could determine the activation energy for the reaction graphically using values of K and T. We're finding the activation energy with values of K and T. This should send off all the sirens in your brain going, wee woo, it's Arrhenius time. So, we're going to write out our equation. We'll do it the one you would use in a graph, which is the one with logs in it. So E equals EA over RT plus log A. That should be a capital, just for everyone who cares about notation. There you go. So we are given values of k and we're given values of t. So we can log k in terms of e. So log ek, that's just what ln means, by the way. I don't know why I wrote it like that. You're going to plot a graph of log k, and in order to find the activation energy we need to bring our temperature over here. How are we going to do that? Well, we're going to times it, but if our gradient is equal to y over x, then in order to do that we're going to have to do log k over 1 over t of log k against 1 over t. Hopefully that made sense, because I just forgot to do it. 1 over t. Then we're going to determine gradient. Determine gradient, and then we're going to have to times it, and then multiply it by gas constant, which we're just going to say in brackets 8.314. Yeah, and that should give us all 3 marks. Solutions of hydrogen peroxide decompose slowly into water and oxygen. This reaction is catalyzed by manganese dioxide. Standard electrode potentials are shown below. Using the electrode potentials to explain how manganese dioxide is able to act as a catalyst for the decomposition of hydrogen peroxide, your answer should include relevant equations. So it's given us 3 here, which we're going to number 1 through 3, and we're going to start by comparing 1 and 2. So we've got 1.51 and 0.7. So the larger one we're going to say is reduced, and the smaller one we're going to say is oxidized, and the oxidized one by convention goes in the reverse direction. So if we were to combine these, we'd get MnO2 plus 4H plus 2E minus plus H2O2 gives us Mn2 plus 2H2O plus O2 plus 2H plus 2E minus. Now what can we do with this? Well, our electrons cancel out, and 2 of our hydrogens from this side cancel out. Does anything else cancel out? No, it doesn't. So our combined equation for 1 and 2 is MnO2 plus 2H plus H2O2 gives us Mn2 plus 2H2O plus O2. Okay, and now if we were to compare 2 and 3. So if we rub this out at the top, this one is going to be reduced, this one's oxidized, so this one goes in the reverse direction this time. So we get H2O2 plus 2H plus 2E minus, I've forgotten everything else, plus Mn2 plus 2H2O gives us, I never have enough space in these kind of things, Mn2 plus 4H plus 2E minus plus 2H2O, and what can we do? Well, cancel out waters, cancel out the electrons, and cancel out 2 hydrogens from this side, so leaves us with 2 on that side, and then make it a nice neat one, H2O2 plus Mn2 plus nothing else gives us MnO2 plus 2H plus and nothing else. So MnO2, manganese dioxide, is reformed and therefore acts as a catalyst. A catalyst. Peroxycarboxylic acids are organic compounds with the COOH functional groups. Peroxyethanoic acid is used as a disinfectant. Suggests structure for peroxyethanoic acid. The COOH functional group must be clearly displayed. So if we do CH, H, and that's connected to another C, and now we've got to make this look like a carboxylic acid. It's in the name, so we're going to double bond to an O, and we'll put an O here and an H here. Now, if this is our extra oxygen, where can this go? Can it go here? Well, no, because if we did C O O, then we just have another bond sitting here doing nothing. And we can't double bond it because then this oxygen would have 3 bonds, so it can't go there. Can it go on the carbon? Well, no, it can't, because CO there, OH here, CH3 here. This has already got 3 bonds around it. So this, would make it 4, and if we did it properly, that would make it 5 and 6. So where's the only other place it can go? Well, if we put it in between the other oxygen and hydrogen, so if we put it here, well, this oxygen has 2 bonds around it, so it's happy. This oxygen has 2 bonds around it, so it's happy. And everything else, this carbon has 4 bonds, this oxygen has 2, this carbon has 4, so everything else is happy. So we know that it's going to look something like, go back to the pen, it's going to be OH like that. There you go. Peroxyethanoic acid can be prepared by reacting hydrogen peroxide with ethanoic acid. This is a heterogeneous equilibrium. Gives us the equation. A 250 centimeters cubed equilibrium mixture contains concentrations of 0.5 molar H2O2 and 0.5 molar ethanoic acid. Calculate the amount in moles of peroxyethanoic acid in the equilibria mixture. How are we going to do this? The same way we do every equilibria. Kc is equal to our products. Now, notice it says heterogeneous. That means we're going to have to get rid of that water, because the concentration of water would be so high that it absolutely ruin our calculation. So our concentration of products, which is CH3COOOH, over concentration of reactants, so H2O2, multiplied by CH3COOH, and these are all raised to their stoichiometric values, which is just 1, 1, 1, and 1. So, what does the question tell us? Well, it tells us the Kc is 0.37, and that's going to be equal to what we want to work out, concentration X, over concentration of H2O2, which is 0.5, multiplied by the concentration of ethanoic acid, which is 0.5, so then we can rearrange 0.37 times 0.5 times 0.5. It's going to give us our concentration of peroxyethanoic acid. So if we get our calculators, 0.37 times 0.5 times 0.5 gives us 0.0925. Now remember, this is the concentration, so this is moles per decimeters cubed. And then what do we need to do to get to just the number of moles? Well, we times it by the volume, which it tells us is 250 centimeters cubed, so 0.25, because we need to convert it from centimeters to decimeters. So 0.0925 times by 0.25 gives us 0.023, to 2 significant figures. This question is about weak acids. Compound A is a weak monobasic acid A student is supplied with 250 centimeters cubed, prepared from 2.495 grams of A. The student titrates 25 centimeters cubed samples of the solution with 0.084 molar sodium hydroxide in the burette. The student carries out a trial followed by 3 further titrations. The diagrams show the initial burette readings and the final burette readings for the student's 3 further titrations. All burette readings are measured to the nearest 0.05 centimeters cubed. It gives us our diagrams, record the student's readings and the titers in an appropriate format. Hopefully you can see that's a table. Calculate the mean titer that the student should use for analysing the result. So I drew the table already just to save us some time, and you'll see here on the kind of y-axis, I don't think that's the right word, but it's got initial reading in centimeters cubed, final reading in centimeters cubed, titer in centimeters cubed, and mean titer in centimeters cubed. So what is our initial reading for titration 1? Well, that's 0.5, so that's going to be 0.60, and you have to do 2 decimal places because that's the lowest resolution. And this is all the way to 23.15. So let's write that in. 0.60. Make sure you keep your decimal places consistent. 0.60, 23.15, 23.1.15. There you go. Titer 2 is the same again, 23.15. And then it goes down to 45.95. So it was 23.15 down to 49.95. No, 45.95 I think it was. Yeah, it was. 45.95. 45.95. There you go. And then titer 3 are going to, what's that? Exactly 10, right on the money. Be consistent with your decimal points, and 32.45. So 10.00 down to, I've forgotten what I said already, 32.45 I think it was. Perfect. So now we need to work out what the titer is. That's just the final reading minus the initial. So 23.15 minus 0.6 gives us 22.55. 45.95 minus 23.15 is 22.8. 0, be consistent with your decimal places. 32.45 minus 10 gives us 22.45. So for this you might just go, oh, it's easy, 22.55 plus 22.8 plus 22.45 all over 3. But you're wrong, because what happens is we need to use concordant results. They need to be within 0.1 centimeters cubed of each other, which in this case is only titer 1 and titer 3. And then you work it out as 22.55 plus 22.45 over 2, and that gives us 22.50, and it's already in centimeters cubed, so we don't need to do any conversion. The structure of compound A is shown below. Compound A has 4 optical isomers. Using this information, the student's results answer the following. Determine the molar mass and the just the formula of the alkyl group, and draw the structure of compound A and label any chiral centers with a asterisk. So chiral centers means all four surrounding groups are different, and 2 chiral centers will create 4 optical isomers. So let's do our titration calculation first. So part 1. MMRNVC. So if we have our compound A and our NaOH, and we know these are going to react in a 1-to-1 ratio because it says in this question here that it is a monobasic acid. So it only reacts to form one water. And then what does it tell us? Well, it tells us that 25 centimeters cubed of this is used, so 0.025, and then sodium hydroxide is our titrated value because that's what's in the burette. It says here. Also tells us the concentration is 0.084 molar. So 22.5 centimeters cubed, so 0.0225, and concentration was 0.084. So that gives us our number of moles, which we're going to do 0.0225 multiplied by 0.084, and that gives us 1.89 times 10 to the minus 3. Now, in order to get the number of moles, I know I said they're in a 1-to-1 ratio, but we're going to have to times it by 10. And why? Well, if we go all the way back to here, it says that the student is supplied with 250 centimeters cubed, which is prepared from 2.495 grams. But they only use 25 centimeters cubed samples at a time. So it's 22.5 centimeters cubed that reacts with 25. So the number of moles for 250 is going to be 10 times as much, which our mass was 2.495. We're going to have to go back and check. I've only just come back down. 2.495. Awesome. So how do we work out our molecular mass? Well, we do 2.495 over 1.89 times 10 to the minus 2, which gives us 132, need my pen, 132, and we'll leave it as that. It's 0.01, so we'll just leave it as 132. And now we need to minus what we know we have at the moment, so ignoring R, what have we got? Well, we've got 2 carbons, so C2, 3 hydrogens, because there's going to be 1 here. So 3 hydrogens and 3 oxygens, which together means 2 times 12, which is 24, minus 3, minus 32 times 3, no, minus 16 times 3, which is 48, and that gives us 57. So what's left is 57, so minus anything that's not R, so just minus molecule except for R, gives us 57. So 57, and we know it's an alkyl group, and we know alkyl groups are CnH2n plus 1. I'm getting ahead of myself. So what can we do with this? Well, we can say 57 is equal to 12 times n, because mass of carbon is 12, plus mass of hydrogen, which is 1, times 2n plus 1, which is just going to be 2n plus 1. We can then move the 1 to the other side, so 56 is equal to 12n plus 2n, which means 56 is equal to 14n. 56 over 14 gives us 4, so n is equal to 4, so the carbon chain is going to be C4H9. So now we have done part 1. So we've got to draw the structure of compound A. I've not left myself a lot of room to do that. I'm just going to get rid of this. So compound A is it's an OH group here. It's across, it's double bond O, OH, and it's our R group. So first of all, this is going to be a chiral center right here, because the OH group there, the hydrogen, the carboxylic acid group, and whatever R is, are all 4 different groups, so that's fine. And then none of these other ones can be a chiral center, so we're going to have a chiral center within our carbon chain. How are we going to do that? Well, we're going to have branches. So if we go C4 straight, so 1, 2, 3, 4, none of those are chiral centers because they've all got 2 hydrogens on them, so get rid of that. If we go 1, 2, 3, and put a methyl there, this methyl and this methyl are the same, so that's not going to be a chiral center. So what our only other choice is to go 1, 2, 1, 2 like that, and then put 1, 2 on there, and then this methyl group is different to this ethyl group. There's a hydrogen in here which is different to the rest of it, and then you've got the whole rest of the molecule which is different. So that is our molecule of A. Is that all the question? We didn't mark the chiral center with an asterisk. The structural formula of compound A is repeated below. 2 reactions of compound A are carried out, suggest an equation for each, and state the type of reaction. In your equations, draw structures for organic compounds. You can use R for the alkyl group. Magnesium ribbon is added to a solution of compound A, and gas bubbles are seen, and the magnesium slowly dissolves. So we're adding a metal to an acid. It's going to do the same thing that metals always do with acids. We're going to form a salt and hydrogen gas. So Mg plus R acid, there's going to be 2 lots of it, because Mg forms 2 plus ions. So OH R double O OH here. That's going to give us Mg 2 plus brackets, going to take away the OH on the carboxylic acid group. Just let me write this out. OH, and there's going to, except there's going to be no H because it's an acid, so it's going to give away a proton. So OH, and there's going to be 2 lots of that, plus, well, what have we got left? We've got 2 hydrogens. So what's this type of reaction? Well, it's going to be redox, because your hydrogen here is going from +1 to 0, and your magnesium is going from 0 to +2. Compound A is heated with a few drops of concentrated sulfuric acid as a catalyst. A cyclic dimer of compound A forms. So you're reading this and you're going, what on earth is a dimer? I've never heard that word before. You've never heard that word before. You know, if you were in an exam, you'd start to go, I don't know what a dimer is, have I missed something on the spec? Oh no, it's all going wrong. But it's okay. What words do you know that end in mer, that have something to do with chemistry? Well, you know the word monomer. What does that mean? Well, it means one molecule. And you know the word polymer. And what does that mean? Well, it means many molecules, multiple molecules. So what does a dimer mean? Well, it's going to mean 2 molecules. And then you want to look at your reactants, or reagents even. You're using concentrated sulfuric acid as a catalyst. So your mind's starting to go, what do we use sulfuric acid as a catalyst in? What type of reaction? So what we're going to do then is we're going to draw out our 2 molecules of A. So double bond O, OH, R. And then we do that again, double bond O, OH, OH, R. And hopefully you can see we've got a carboxylic acid group and we've got an alcohol. And what do we know that that can do with sulfuric acid? We know it can form an ester. And in this case, it's going to form a cyclic kind of ester. So let's just draw an arrow, put H2SO4 over the top to show that it's a reagent. So if we do our R molecule here, that means we're going to do an O group here. That's going to bond to a carbon that has a double bond, so that's going to bond to this one here. That's going to go across, form another R group, form another O bond with that, and then that's our completed molecule. That's it. It looks a lot harder than it is. All it needs is just for you to take your time. And then obviously we need our other product, well, we form two esters, so we're going to form two water. What's this type of reaction? Well, it's esterification. You can also say condensation for the mark. The mark scheme says either is absolutely fine. Chromium-3 picolinate shown below is a neutral complex that can be prepared from the weak acid picolinic acid. Picolinic? I don't know. Chromium picolinate is used in tablets as a nutritional supplement for chromium. Draw the structure of the ligand in chromium-3 picolinate. Well, first of all, little hint in the question here, we're going from picolinic acid to picolinate. So that suggests that we're going to have an O minus in there somewhere. But let's pick this apart. We've got three ligands. We've got one here, and one here. Get rid of those circles because they're massively in the way. And we know that the charge on the chromium is 3 plus. Tells us so here. So from our three ligands, each one is going to have a negative charge, one negative charge to be specific. And when you look at that, it's going to be our O minus. So if we put an N here, and all we're doing is drawing the molecule that we see in front of us. This is a very poor drawing. My hand is shaking an insane amount. But it's going to be that. So have we got one negative charge? If we repeat that 3 times, yeah, we'd have 3 minus. That would be neutral, which the question says it is. I can't remember where it says it's neutral. Neutral complex. There. Awesome. Next question. A typical tablet of chromium-3 picolinate contains 200 micrograms of chromium. Calculate the mass in grams of chromium-3 picolinate in a typical tablet. 1 microgram is 10 to the minus 6 grams. Give your answer to 3 sig fig. So it's given us the mass of something, and it wants us to find the mass of something else. What does that remind you of? Well, literally any other kind of reaction calculation you might do. Just going to do our MMRN grid, like always. So 200 micrograms, 200 times 10 to the minus 6 of chromium. Keep doing capital R. So what's our MR of chromium? Well, that's 52. So that gives us our number of moles of chromium. So 200 times 10 to the minus 6 over 52 gives us 0.0. Okay, so 3.85 times 10 to the minus 1, 2, 3, 4, 5, 6. So that, because we have one chromium per complex ion, our number of moles is also going to be equal to our number of moles of complex ions. So then we need to work out the MR to give us the mass. So 52 plus 3 lots of the ligand. This is going to be difficult. So if we go back up, let's just do what we know first. There's 1 nitrogen, there's 2 oxygens, and there are 1, 2, 3, 4, 5, 6 carbons, and then hydrogen here, hydrogen here, hydrogen here, hydrogen here. No hydrogens here, this carbon's got 4 bonds, no hydrogen here, so H4. What does that make the molecular mass of this? Well, 14 plus 32 plus 72 plus 4 gives us 122. Times by 3 gives us 366. So 122 there. So 366 plus 52 gives us 418. So that's 418 total. So then we do 418 times 3.85 times 10 to the minus 6. And that gives us 1.61 times 10 to the minus 3 grams. This question is about organic molecules that have a strong smell. Thiols are foul-smelling organic sulfur compounds with the functional group SH. Butane 1 thiol shown below contributes to the strong smell of skunks. Way! OCR shout out. We love that. Thiols are weak acids, right? The expression for the acid dissociation constant for butane thiol. So, what's our Ka normally? It's going to be our concentration of H plus our conjugate base, so A minus, over our whole molecule. Now, these carbons are bonded very strongly to their hydrogens, so it's not going to lose those hydrogens. Which hydrogen is it going to use? It's going to lose this one here. So if we get rid of our writing here, if we just get rid of the H here and the A here, we're going to write it in specifically for us. So H plus is fine. Concentration of conjugate base, which is going to be C4H 9S minus, over the whole molecule, which is just C4H10S, and no charge on that. Thiols react with carboxylic acids to form thioesters. Write an equation for the reaction of butane 1 thiol with ethanoic acid. Use structures for all organic compounds with the functional group clearly displayed. So butane thiol is 1, 2, 3, 4 SH plus ethanoic acid, which is, we're going to draw it the other way around. That's awful. Like that. Double bond O, OH here. What can you see? Well, OH group and an H. That's going to form water. So it doesn't ask us to include reagents, which is good because it doesn't tell us and we don't want to guess. So what's that going to do? Well, if we take away this oxygen, this hydrogen and this oxygen and hydrogen, it's going to leave us with sulfur bond between them. Put that back because we don't want to lose marks. So that's going to be 1, 2, 3, 4 down to the S, and then the S is going to bond to a hydrogen. What's going on? S is going to bond to a carbon, which is double bonded to an oxygen, which is like that. When beer is exposed to light, 3-methyl-but-2-ene-1-thiol is formed, which gives an unpleasant smell and flavour to the beer. Draw the skeletal formula for 3-methyl-but-2-ene-1-thiol. So our first job is to draw the but. So 1, 2, 3, 4. Okay, 1-thiol, SH, but-2-ene. So if that's position 1, this is position 2. So draw double bond in here, and then 3-methyl, if that's 1, that's 2, that's 3 methyl group there. Propane 1,3-dithiol reacts with carbonyl, that's C double bond O molecules, in a condensation reaction to form a cyclic organic sulfur product. Write an equation for the reaction of propane 1,3-dithiol with propanone. So draw these out. Propane is 1, 2, 3. And then SH, SH, and we're reacting that with propanone, which is that. And that's got to form some sort of cyclic compound, something like that. So let's look at what we've got here. We've got an H group on the end, and we've got an oxygen. Well, if we do that, we can form water. And what would that leave us with? Well, it'd leave us with S there, that'd be S minus, and you'd also be stuck with 2 plus carbon here. Sulfurs could bond to this carbon here, and that would leave us with a sort of ring shape, and then 2 stick out methyl groups. So let's just draw that. Basically, we're taking this and we're folding it, so it's going to form that's 1, that's 2, that's 3, that's 2, that's 3, You go straight to sulfur, which are going to bond to the group like that. So let's just replicate that. Easier said than done. Yeah. Doing inconsistent lines, and it's not helping. 1, 2, 1, 2, 2. Thank you. S, S, into there, like that. Last question. The structures for 6 naturally occurring organic compounds with pleasant smells, B to G, are shown below. The common names in brackets relate to their source and smell. Explain how chemical tests would allow each compound to be distinguished from the other compounds. In your answer, include essential details for all test procedures and observations. Details of apparatus and quantities are not required. So, first of all, what are we going to do? We're going to see what functional groups we've got. So on B, we've got C1C, and we've got a tertiary alcohol. On C, we've got C1C, and we've got an aldehyde. On D, we've got C1C and a primary alcohol, primary OH. On E, we've got no C to C double bond, and instead we've got a ketone. On F, we've got no C to C double bond, and instead we've got a secondary alcohol. And then G, we've got C1C and a ketone. Okay. So, what's the first easiest way to separate them out? It would be separating the saturated compounds and the unsaturated compounds. So we're separating E and F from the rest of them. So, we can separate E and F. Using, well, how do we distinguish? Alkenes, we use bromine water. Br2, which E and F, from the rest. We're not separating them from each other just yet. From the rest using bromine water, which will not change from orange to colourless. As no C to C double bond is present. So now we've separated E and F from the rest of them, we need to separate E from F. So to separate E from F, we need to go back to the question. So one's got a ketone, one's a secondary alcohol. I'm just gonna do separate E from F. Use acidified potassium dichromate K2Cr2O7 /H+, which will turn from orange to green. For which was the one with the alcohol? Hate questions like this because you always have to go flip the page back and forth. Which one was the alcohol? F, which will separate for F as it contains a secondary alcohol, but E does not. Right. So that is E and F separated. So we now know what E is, and we now know what F is. E and F we can get rid of. What's the next biggest difference we can do? Well, we can separate the aldehydes from the alcohols. So we're going to use, what are we going to use? We're going to use 2,4-DMPH, or DMP, depends what you call it, to separate C and G from B and D. So, separate C and G from the rest. Realistically, there's only 2 left, but we'll say the rest using 2,4-DNPH. DNPH, which will turn from an orange solution to an orange precipitate, from an orange solution to an orange precipitate, due to the seed to double bond O group present. And then how are we going to distinguish C and G? Well, one's an aldehyde and one's a ketone. So how do we distinguish those? We use ketones. So distinguish C from G using Tollens reagent. Tollens reagent, which will form a silver mirror for at 50 degrees for which one is it? Which one is our aldehyde C? For C, but not for G, as C contains an aldehyde group. And then, finally, so we've now separated C and G, so the only ones we have left to separate C and G are B and D, and that's nice and easy. We've got a tertiary alcohol here and a primary alcohol here, and how are we going to do that? We're going to use acidified potassium dichromate again, and I've already written it here because I didn't want to write it out. So distinguish B from D using acidified potassium dichromate, as this will turn from orange to green in the presence of D, as it is a primary alcohol, but not for B, as it is a tertiary alcohol. And that's all your tests done. There are loads of ways you can do it. Literally everyone I saw do this had a different way of doing it, and loads of them were right. The mark scheme for this question was absolutely huge, so take your pick. And that is the question paper done. I'll leave you to other me to see you out.
So that is it for the 2017 papers, and that's also going to be it for me for a while. I'm going to do a video next week on the dates I'll be back, but I'm going to take a bit of a respite because I'm going to be revising for my A-levels. Next week's video will have all the dates that I will be back for. I really hope you enjoyed. I really hope you found this helpful. As always, if you have any questions, leave them in the comments. Remember to like and subscribe. 2 fun facts for you. When I was editing this, I got about halfway through and fell asleep. And then when I went back to edit it after a power nap, all my audio for the second half had disappeared, so I had to re-record all of it within the space of about an hour last night. So that wasn't fun. But I do it for you guys because I love you all. So I really hope you enjoyed. Thanks for stopping by, and I'll see you hopefully next time. Bye.